righty. Good morning, everybody. So let's get started on chapter 2 of today's lecture. But before we do so, any questions so far? Anything that we should make a note of? I'm sorry, questions on chapter 2?
Yeah, I believe so. I just had it pulled up.
Oh, you mean recitation worksheet? That one?
There was a folder like that. I don't know. There were
Yes.
questions listed on there, and I just figured they were like study guide questions.
Oh, I see what you mean. Oh, you're referring to the resources and information. Yes, so those are the learning objectives for this chapter. It's also a guide for you to sort of just check whether or not you've understood the concepts, because that's what we're trying to achieve with this module. So
Nothing was turned in recitation.
No, not at all. You'll get worksheets printed out for you in recitation, and those are a completely different set of questions, and there won't be that many questions on your recitation worksheet. It's really just a guide to help you and the recitation TA sort of just go through some of the bigger points, the highlights, and also go through some rigorous computation as well, not just hit the major points, but they are the broad themes of the topic. So hopefully that answers that. Yeah, and it's those questions. The learning objectives are quite helpful too when you're studying, because those points should have been communicated during these 2 lectures. Anything else before I go on? All right, in that case, then let's proceed. So chapter 2 is on atomic bonding, and I didn't ask your name, the person who just asked me a question. Okay, so Kenzie just asked about the module on Carmen. So that's how the organization of the course is going to be. Typically, we start off with learning objectives, so you can just go over those questions, before a module starts. And of course, all the lecture slides pertaining to that module, most likely just the chapter itself, will also be in that section. And then all the lecture videos will also be in that section. And if there's anything additional besides the recitation worksheet that pertains to that chapter that maybe we've discussed in class or I've brought up independently, all of that will be subsumed under that one module so that you don't have to go to multiple places to find different things. And if something's not there, it's probably just a clerical error. Somebody didn't click publish or something like that. Just alert us and we'll get it on as soon as we can, but we try to avoid those sort of mistakes. Okay, chapter 2 will be the foundation of the discussion of how atoms pack, which will be in chapter 3, and how atoms pack will lead to mechanical properties. That will be chapter 6, but those rely on whether atoms pack perfectly in a crystal or imperfectly in a crystal or not in a crystalline lattice at all, and that's chapter 4, and then how atoms move around, that's chapter 5. So for the next 4 chapters, we're going to be talking a lot about where an atom is and how that affects the overall macroscopic properties that you observe. And you may notice that there's a little bit of review from your intro chem as well as your intro physics lectures. And so we want to review it because it gives us a good start and a good foundation to start talking about properties within material science. So we'll review the type of bonding, the classifications, how strong they are, if there's directionality to each bond, and of course, as you may have seen in your lecture slides, this will affect properties such as the melting temperature, thermal expansion, elastic stiffness, right, when we talk about mechanical properties, electrical and optical properties as well. One of the most simple models, without going into great detail about quantum mechanics, which some of you have a background in that, which is great, and you can derive what S actually means, what P actually means. But for the purpose of this intro class, the foundation that you need is just to understand valence electrons and where they are, and and how that affects how cations or a zero valent atom can interact with its neighbors. And so we'll just refer to some of the simpler terms in quantum mechanics on how to describe electronic configuration for an atom. And you may have seen this already, where we can discuss electronic configuration for each atom through their quantum numbers. The first is n, which is your principal quantum number. That tells you the size of your orbital, your atomic orbital. And then there's m, and that's often referred to as that's often referred to as S, P, D, F, and so on and so forth. And those letters have historical significances. Obviously, they're not in alphabetical order, but that tells you the angular momentum. So for the purpose of this course, you just need to know what they are. We will not be deriving them in this course, but of course, there's a rich history and rich physics behind the significance of these terms. And of course, you need to know, the components of an atom, of course, the nucleus, which has the proton, right, and the number of protons and number of neutrons gives you the atomic number or the atomic mass in AMU. And if there are differences in the number of neutrons versus the number of protons, right, that gives you an isotope. And you may have heard of carbon dating. That gives you a timeline of how old a material is when someone detects the ratios of carbon-14 to carbon-12. Right? So isotopes are quite useful scientifically. They can be unstable as well. So they can be quite radioactive. And so that's also a huge area of physics research. But for the purpose of chapter 2, you just need to know what an electron is, what a proton is, what a neutron is, and of course, how do you get the atomic mass when you look at a periodic table. Okay, so this is the planetary model. It's quite simple. You start off with, the n equals 1, n equals 2, n equals 3, and generally that just goes with the size. That would be the most simple case without getting too detailed and intricate about that. You also need to know the differences in energy, how these orbitals build up, right? So 1s is lower in energy, lower in this scale, but highest in energy magnitude-wise if you're trying to eject an electron from that orbital because it's a core orbital, right? It's being held in by the nucleus. We won't go into detail beyond that. So then you can see, for each orbital, you have the 1s can fit 2 electrons. 2s can also fit 2 electrons, as denoted by these dots here. Sometimes you've also seen them in chemistry or physics drawn like this, right, because of the Pauli exclusion principle. That gets into more spin states, but basically you can fit 2 electrons in each orbital for the s, and then 6 for 2p, as you see here. So 1, 2, 3, 4, 5, 6, and then 2 again for 3s, and then 3p. 2 again for 4s, 10 for d, and back 6 again. So on and so forth. And you may have learned a trick of how to actually look at the periodic table and do the zigzag and build that up. You don't really need to know that here. You're not expected to memorize how the electronic configuration is built up. If you're asked about that on an exam, say, you would be asked more about the generalities of the group that they're in and not specifically just build the electronic configuration as you would have done in Intro to Physics or Intro to Chemistry. One thing to note is that these are discrete states of energy, right? So this is a result of years of quantum mechanical research. This is just what we're going to take as a given. We also want to highlight unreactive species. So we'll talk about, atoms and ions. Those are charged states, right? They're either positively charged or negatively charged. There are also atoms, elements that don't necessarily want to react. They're unreactive for the most part because their shells are complete. Let's say helium, 1s2. There are 2 electrons in the shell. It's free unreactive. There's nothing else to do. So it's called a closed shell configuration. That's not in your textbook, but that's often what it's referred to, a full shell or a closed shell configuration. Same thing with neon, same thing with argon, same thing with krypton. That's not to say they're not reactive all the time. Of course, you can induce a reaction with enough pressure, enough temperature, what have you. You can always perturb a system to get it to do what you want to do. But for the most part, if we're talking about standard temperature, pressure, these are the given states of these elements, okay? And of course, if we talk about any extreme conditions, any perturbations, we would be very upfront about that, and we wouldn't, try to trick you or anything like that. And for the most part, scientists and engineers are very upfront and quite transparent about the assumptions or any conditions that are not deemed as, obvious, like standard temperature and pressure. So if you see here, you can start to build the elements, you can build the electronic configuration up as you go through, the atomic numbers from 1, hydrogen, up to helium, 2, lithium, 3. We've talked about lithium, understanding its electron configuration and how it behaves as a cation is actually of utmost interest to most battery people, because that's mass transport that you're worried about. You're worried about moving one ion from one electrode to the other and then moving it back. And that rules everything, every portable device that we have, understanding mass transport of that one ion, right? And so understanding how the electron configuration works plays into that. And then, of course, we continue with beryllium, boron, carbon, and so on and so forth. So this just gives you an example and hopefully is a reminder of what you learn in terms of building up the electron configuration for these elements. And the outer shells, highlighted in blue here, are the valence shells. Those are the outer shells. So when you react, let's say, a cation with an anion, those charged species, the electrons are being shared or transferred there. It's often not of course, the core electrons that are part of that bonding. And then when we also talk about bonding, we also talk about electronegativity, which is really a formalism that Linus Pauling has come up with, and it's held up pretty well over the years, this numerical system where you have high values of electronegativity here, and that means it has an affinity for electron, right? So that means anions from this side tend to react with cations from this side, and that means the elements on the left side of the periodic table tend to be cation. They want to give up the electron, either 1 electron, 2 electrons, and then, of course, the elements on the right will become anions, and, of course, they will accept those electrons in such a bonding. And that's denoted as here. Now, I drew some general arrows that you see here, more electronegative elements, more electropositive elements. There's really no, well-defined line of what's, less or more, but it's really a scale. So it's something more or less electronegative. And so you can see here again the periodic table. The range is about 0.7 to 4, and as I've just said, the larger number tend to have a tendency for the element to acquire electrons, so they're going to be most likely anions. And same thing, the trends tend to go like that. Where you go to the right of the periodic table, you get larger electronegativity. To the left, you get smaller electronegativity. And if the differences in the electronegativities are quite large, it's most likely not going to form a covalent bond. It's most likely going to form an ionic bond where there is charge transfer, and that's something we'll go into great detail later in the chapter. Once again, there isn't like a sharp cutoff. If it's 2.1, it's always ionic. That's not the case. The general rule of thumb is that if the electronegativity difference is 2 or less, it's most likely going to be a covalent bond. That's the general rule of thumb. Of course, there's always exceptions, and there's also could be mixing of bonding character, right? So this is a good start. This is a good scale to work with, but it's not the end all and be all. It is, however, for this class, I realize this is intro class, so we won't get into subtleties and nuances and major exceptions, well, other than big ones. But we won't get into all those details in this class, okay? And if there's an exception, obviously that would be noted. Not trying to trick you or anything like that. Okay, so in the 5-6 sections of Chapter 2, we discussed the 3 types of materials, and we also discussed the 4 types of bonding. So we'll start off with the 3 primary classes of materials. But before that, we'll get started here. Okay, let me see. It should be already in. Let me see. Wrong one. Here you go. Polymers, of course, is one of the 3 types of materials. Yes. Okay. Well, just take a screenshot and email Natalie. Yeah. Okay. I'm sorry? Oh, just email Natalie. Okay, so any volunteers in regards to their sharing their answer? Yes, sir.
I think it's letter C, because polymers are these giant chains of monomers, so the most common bonds that would bond together would be covalent bonds, and then you'd have the van der Waals forces between the chains, which would be your secondary.
Thank you. What's your name?
Zachary.
Okay, Zachary. I'll repeat Zachary's answer in case you weren't able to hear it in the back. It is C because polymers have covalent carbon-carbon bonds, and as well as van der Waals bonding in between the chains. So thank you for that. Let's see. All right. So we're improving in percent correctness, which is great. So we'll cover this in great detail as we go on, but that's just to see if you've read beforehand. Right. So we'll first, before we get to all the details of bonding, we'll talk about the three types of materials. So we've sort of discussed this a little bit on the first day of lecture, where I mentioned the three classes of materials: metals, ceramics, and polymers. Lecture 2, you also saw some examples that have revolutionized society and industry there. And so we'll go over some of the properties as well as some of the bonding that occurs in these classes of materials. So I'll go over them in detail as you see here. So in metals, we've discussed structural steel, right? So some examples of metals in applications are steel beams, copper wiring, automobiles. We've also talked about cobalt, lithium. So there are a lot of examples of metals in the periodic table. In terms of the properties, metals are ductile, they're conductive, right? We sort of know colloquially that copper is conductive and it's used in wiring. They're dense, strong, reflective. Usually we describe metals as having a sheen, right? That has everything, that optical property has everything to do with how electrons are packed. And their melting point is moderate relative to that of ceramics. It's not too low, it's not too high. That's what I mean by moderate. It's relative to that of ceramic melting temperature. And the bonding is described as metallic bonding. Ceramics, we've seen some examples with alumina used in housing for lighting, for lamps. Other examples are, ceramics are used in pottery, bricks, concrete. We've talked about how cement holds everything together, but the processing of ceramics can be quite energetically costly. The glasses and other gems, minerals that you find, that falls under ceramics. In terms of properties, they're brittle. They can be strong, but brittle. Electronically, they're insulating. There's a range of densities based on how the atoms are packed. And so we'll talk about the range of coordination number there later on in the chapter. They're strong, as I mentioned, and we've also talked about how they can be opaque or transparent, and their melting temperature is quite high relative to that of metals. And the bonding character in ceramics can be just ionic or ionic and covalent bonding. Okay? There can be a mixture of bonding types. And as Zachary has mentioned, polymers, right, can have covalent and secondary type bonding. Some examples are everyday household items that you already know, such as plastics, rubber in your tires, those are thermosets, gels in your in food and coagulating food. So if you've ever had ranch dressing or frozen dinner, you've eaten alginate cross-linked polymers and you didn't know it, or maybe you did know it, but they're derived from kelp, actually the film that's on kelp, so it's organically derived. Foams as well, polystyrene. So really household items that we already use or even eat. In terms of properties, they can be ductile, they can be brittle, they can be insulating, they can also be somewhat conductive, and that was also a Nobel Prize that was given out for conductive polymers. Density is relatively low because of the secondary bonding. They're not as strong as the other two materials, and they can also be opaque or transparent depending on the crystallite size, and we'll talk about how to manipulate that in chapter 12 when we talk about polymers and composites. And the melting temperature is relatively low because you can break the secondary bonds more readily, because those bond energies tend to be much lower by 10x than, say, a covalent bond. Right? So all these properties derive from the way atoms are bonded in these types of materials. Yes?
So you said they were low density, polymers were low density because of their secondary bonding.
Mm-hmm.
Seems kind of counterintuitive.
Yes. Oh, okay. So clarification, the question is, it seems counterintuitive that polymers are less dense because of secondary bonding, because there's more bonding. I should clarify, when I say secondary bonding, I mean a type of bonding, not that there are more or less number of bonds. So I hope that's clear and not confusing. It's just a type of bond. So I'm talking about bond energy when I say secondary, okay? In terms of the 4 types of bonding, they are listed here. And I've also listed, just to remind you, the different types of materials that they occur in. So once again, metallic bonding occurs in metals. The electrons are delocalized in a cloud. You may have heard that already in your Intro to Physics course. You can sort of think of it as an electron cloud around cations. That actually is counterintuitive. But if you think about a sea of copper atoms or a sea of nickel atoms and you treat the delocalized sea, right? So copper is 2+, nickel is typically 2+. You could think about, the 2 electrons are, sorry, that's in the ion form, but you could think about if there's a sea of electrons, right? They have to interact with some cation. So in your book, there's a figure where it's a copper 2+ and then delocalized sea of all the 2 electrons floating around. That's one way to think about it. You can also just think about it as an electron gas or electron sea. So the electrons are around that atom typically. It's just now delocalized. That's all it is. But I wanted to explain that figure, why your book drew a figure of a metal that's actually copper 2+, and then they say it's metal. That's the reasoning behind that. In terms of covalent bonding, they often occur in ceramics and polymers, as we just discussed. The electrons are shared in between the 2 atoms. They are directional. So when you think about carbon and diamond, that's an example we'll go into detail. That's sp3 hybridized bonds. The electrons are shared in that type of bond, right? If you have a double bond, that's sp2, and that's more planar, right? So it's directional, and these bonds are strong relative to that of metals. Ionic bonds occur in ceramics, and they're transferred. This bond, in order to form this bond, you need an electron transfer from one ion, the cation, to the anion. The bond is strong, and they occur between the smaller atom, typically the cation, and the anion, which is typically the larger ion. And then, as was mentioned, the 4th type of bonding is secondary. So these are called, as Zachary mentioned, van der Waals type bond or London dispersion forces. Hydrogen bonding is a type of secondary bond. So the energy, the bond energy is just it's just smaller. That's all. So they're typically weaker as well. So when we talk about bonding types, we talk about we talk about if an electron is shared or transferred. So the bond type, what's happening to the electron? Are they localized or free to move? So is it delocalized in a metal, or is it just in between the cation and the anion, or is it shared in its covalent bond? We talked about bond directionality. We talked about bond energy. So these are the 3 things that you need to think about when you think about bonding types. Right? So in terms of bond energy, I refer to secondary bonds as low energy. So covalent bonds are typically 200, 700 kilojoules per mole. They're much stronger than, say, a typical hydrogen bond, which would be 20 kilojoules per mole or so. All right, so with that, we'll move on to the details of metallic bonding in metals. Some of the key features that you should know about metallic bonding is that they obey the hard sphere model. And what that means, and there's a figure in your book that shows the planetary model, the hard sphere model, and then the more quantum mechanically appropriate model, which is, the electron cloud is sort of diffuse, and it's not really, so rigid. For the purpose of this course, we'll mostly deal with the hard sphere model, where when we talk about an atomic radius, we really mean the center of the atom to the outer shell. You know, obviously there are more subtleties in that, but that's beyond the scope of this course. And so you're not responsible for that. Metallic bonds are moderately strong, as is mentioned. The ionic and covalent bonds are stronger, and of course secondary bonds are weaker. They are shared, so this goes back to, the electrons are shared, so this goes back to the delocalized C model, and they don't really have a preferred orientation in the way covalent bonds are. Of course, there can be, atoms can pack in a certain way, and we'll talk about that in chapter 3, but they don't really have a preferred orientation, and they can actually, you know, move and slip and slide and contain defects quite a bit, and we'll talk about that in defects and mechanical properties. So you see here the highlighted elements that have metallic bonding character. So those are typical. You see lithium, sodium, those are soft metals. You see also elements that have bonding characteristics like iron. You think of steel, right? Carbon dope iron, cobalt, chromium, you know, typical metals, of course, gold, silver, palladium, platinum, that's a catalyst in your cars. And, and here is the figure that I was mentioning in terms of the description of how the electrons are delocalized amongst all of these copper atoms. So metals take up a huge portion of the periodic table. So it's quite important as a class of material and a bonding type to think about if we want to manipulate these materials so that, you know, they can be stronger or more ductile or what have you. In terms of ceramics, we'll talk about ionic and covalent bonding. Here I put or, but sometimes they can also be and. And so we'll talk about that. In terms of ionic bonding, the two requirements, actually 3, are that you need charge balance. So we talk about this transferring of electrons from the cation to anion, and that's great, but you need to transfer the same amount, right? So there needs to be charge balance. So the example that you see here is calcium fluoride. Calcium is a 2+ cation, and fluorine becomes fluoride, which is negatively charged, -1 charge. And so you would then, of course, need 2 to charge balance every 1 calcium cation. That's a 2+. Okay, so there that's reflected in the stoichiometry that you see here. Some call it calcium difluoride, I call it calcium fluoride, but that's under the assumption that you've already charged balance in your head, so I don't have to tell you that, right? But if you wanted to be explicit, you can just say calcium difluoride as well, but when you're in the field, that's sort of unnecessary. The crystal structure also needs to be stable, so depending on the ratio of the cation size as well as the anion size, so the radius of each of the ions, you can have unstable coordination numbers and stable coordination numbers, and there's a range of that. Depending on that ratio, you can have 2 neighbors, 3 neighbors, 4 neighbors, as you see here. So if a cation is too large for a certain anion, it will be unstable, right? If it's too small, it will also be unstable. So there's a chart, there's a table in your book that goes through, you know, what is the range for each stable coordination number. And as I mentioned, you need also electron transfer between the 2 ions with differences in electronegativity. Another example of ionic bonding occurs in sodium chloride. Here you see the sodium 1+ cation, the chloride 1- anion, and the electron transfer occurs as you see here. Because one is negatively charged and one is positively charged, there will also be Coulombic attraction. And so these forces will also dictate the stable atomic distance between the two ion centers. And the other examples that you see here from the periodic table, magnesium oxide, calcium fluoride again, cesium chloride. So these are other salts that have ionic bonding type. In terms of covalent bonding and structure, we've just discussed how there's covalent carbon-carbon bonding in polymers. There can also be a covalent component in SiO2. Right? There's some electronegative difference there, but there's both ionic and actually covalent characteristics in glass. In covalent bonding, the valence electrons are shared. They're not transferred between the two atoms. The bonding is directional. So as I've mentioned, in diamond, it's sp3 hybridized, so that means those orbitals are at a particular angle, and so your electrons are shared in those orbitals at that particular angle. And because they're shared, the bond length is not necessarily the sum of the radii, but of course, if you were asked to compute that, you would be given a table. The electronegativity values are comparable. They're not so different relative to that of ionic bonding. And as you see listed here again, they can be present in ceramics, semiconductors like silicon, and polymers. Here you see a polyethylene chain, right? And we'll go into detail about that, where N describes the number of mers or monomers. And here is methane, CH4, and you can see sharing between carbon and hydrogen, and they're denoted as sharing like that. In terms of covalent bonding, you can see that in between silicon and carbon, so silicon carbide, one of the hardest materials out there. You could see it in between two chlorine atoms, in chlorine, Cl2, which is a very toxic gas. You could also see in fluorine as well, F2, diamond, sp3 hybridization that we talked about, H2O with a permanent dipole. I mean, the list goes on and on. There are a lot of materials have covalent bonding that's out there. In terms of polymers more specifically have covalent and secondary bonding. So we'll talk about secondary bonding in this context. When water melts, the first bond that gets broken is the secondary bond, right? Because that's lower in energy. So what specifically is that secondary bond? That's referred to as hydrogen bonding. And so that's the bond between the hydrogen and the oxygen, but they're not from the same molecule. This hydrogen is on this molecule, this oxygen is on this molecule, and when water, or I should say H2O melts from ice to water, that's the first bond that breaks. Okay, and so that allows then the ice to reconfigure all of its H2O molecules to, well, really whatever form it wants, right? Whatever container that you may have it in. And so that's depicted here, as you can see. I've also drawn in the permanent dipoles in H2O, as you see here in red, that I've just drawn over. And so that's counterintuitive because it's the reason why H2O is less dense when it's in ice form versus when it's in water form. Because of this hydrogen bonding, it's actually, when it becomes ice, it makes it form this open structure that you see here, right? So if you have a somewhat positive hydrogen that's here, when it has a secondary bond, it has to attract an oxygen in a particular coordination, in a particular direction, as you see here. And so in order for ice to form, the solid H2O has this open structure, so it's less dense. And when it melts, it can reconfigure in whatever way it wants. And so that's why you see ice on top and water below, right? That's not typical of other metals. When they melt, they actually become more dense, right? So, sorry, when they solidify, they become more dense. I flipped that. So hydrogen bonding is actually quite important, quite an important bond, and it's the reason why fish don't freeze to death in ice, right? Because the ice floats on top. To have secondary bonding, that doesn't have to be just in molecules with permanent dipoles. So I brought up the example before where there's the noble gases, right? Helium, argon. They can have fluctuations in their electron density, as is any atom. Everything is always in constant flux, in constant motion. Everything's atomically vibrating because we're not at 0 Kelvin. We're at 25 degrees C, right? We're at 298 Kelvin. So everything is in flux just a little bit. So at any instantaneous point, there can always be a slight induced dipole in your atom, even if it's a noble element, right? Even if it's argon, the electron density can always flux a little bit. And if that's the case, then its neighbor will experience that flux by just a little bit. So you'll induce a very slight dipole. And if you manipulate it right, you can actually get them to attract one atom to attract the other by just a little bit. But those types of energies, if you're talking about the secondary bonding in an argon-argon atom, you're talking like 0.9 kilojoules per mole. So that's quite small and honestly pretty insignificant when you're talking about a carbon-carbon single bond that's 700 kilojoules per mole, right? So, but it does exist. It's not zero, okay? And so here I've listed the types of the different secondary bondings where it goes from weaker secondary bonding to stronger secondary bonding. So hydrogen bonding here, fluctuating induced dipole that I just mentioned there. And as I've said, hydrogen bonding doesn't just occur in water. It occurs in anything really with hydrogen. So here you see an example. Everything with hydrogen, but that's qualified. You see here an example of HCl where this can be somewhat negative. This can be positive, and I draw this delta just to denote that it's a small change. And then there can be hydrogen bonding in between those two molecules. Yes?
What's the difference between photomolecule-induced dipole and permanent dipole?
So water has a permanent dipole, right? The H2O that you saw in the previous example, right, has a permanent, that's a permanent dipole. So a polar molecule like HCl can have an induced dipole like this. And then this would be more like the extreme example where you can induce something. This can also have an induced, so this is also fluctuating induced dipole, right? There shouldn't be a dipole in between two atoms that are alike. But because the electron density is always fluctuating a little bit, you can have that induced. Okay.
So the vectors describe positive to negative?
Yes. Yes. Oh, this is a little mislined, so I will correct that. But the secondary, sorry about that. It's a little bit mislined. I'll correct that and upload a better figure for clarity. In terms of polymerization, we discussed this just very briefly, where it basically describes bringing together, most likely in a chain form, many mers or many monomers. And so there you can have different starting monomers, different subunits. Here is an example of an ethylene molecule where there's a double bond between the two carbon atoms. And then each carbon atom is bonded to a hydrogen atom covalently. And so here you have covalent bonds in the molecule. And in order to form a polyethylene polymer, you need to break this double bond. You need to break the covalent bond. Then you need to form the single bond. And then you need to make a whole chain. You need to repeat this. So typically, when you make a polymer, you need a catalyst of some sort. And so there it's called radical polymerization, where you have maybe a metal catalyst that will initiate this radical that will break the bond, and then that allows this to be a very reactive species that will then react with the next radical that it sees, and then they will form the bond that way. And so you can just go through this process until you run out of monomers. There are a lot of people working on this to understand how do we control the degree of polymerization, right? What if we don't want the reaction to go to completion? What if we want to cross-link these mers in different ways? What if we want to cross-link two polymers that we've already formed in different ways to form Kevlar, to form Teflon, to form nylon, what have you, right? So how do we control this so that we can get the functionality out of this? And so even though this is quite a simple process that you see here, break double bond, form single bond, terminate process, the termination of this process is actually the holy grail, right? Can you control it? If I asked you to make N equals 500, I just want 500 monomers instead of 1,000. Can you control that process? That's really key in polymer science. And that controls a lot of the items that you have in your house and that you eat as well. And in terms of the energetics of polymerization, in your book, there's a table that lists all the bond energies that are of interest in this chapter. And so if you take an example of polystyrene, so you see here one of the hydrogen has now been replaced by this ring. And this is now the styrene monomer. So the polystyrene, it's the same thing. You start off with a double bond that you have to break. Here, it's going through radical polymerization. So you have a catalyst that will induce this radical formation. Now you have a radical that you see here. And then that monomer will go find another monomer. And then now you have two mers, or a dimer. And it still has a radical, and then it will just go on and so forth and form longer and longer chains. And you hope that it forms in a linear fashion, right? When it doesn't stop in the middle. Now, if these two dimers find another two dimers, then you will have four mers, and the process could actually just stop. If these two radicals see each other, they make a bond, and then it just stops. So the purity of your polymer, if I ask for N equals 500, I want you to make a chain of 500 monomers, sometimes you'll actually have, a lot of times, you'll actually have a distribution. Sometimes you'll have 4 mers, sometimes you'll have 5. That distribution is highly unwanted for the most part. You really want to control the degree of polymerization very tightly. Otherwise, you have a distribution in mechanical properties. That's not always desirable. So for the energetics, when we think about the reaction, we think about, okay, well, we have to break the double bond. That's listed in your book as 600 kilojoules per mole. To form the single bond, you actually get 2 carbon-carbon single bond out of it. And each carbon-carbon single bond is 370 kilojoules per mole. So 2 of those would be about 740. And as you remember, the reaction energy is just the products minus the reactants, and that gives you the difference. I should also note that the fine print in table 2.2, I believe, says that the product energy is often negative, and the reactant energy is denoted as positive. If you treat it as so, you would actually have something that looks like this, right? Negative minus that. So you would actually get negative 1,000 or so kilojoules. I want to clarify that and just say that you can just keep the positive, and then you can also denote that that's the amount of energy that's released. Okay, I realize that can be confusing. Is it positive? Is it negative? We're interested in the magnitude, and if you can just explain that it's, you know, that this is the process and its release, that's clear enough for me. So I wanted to clarify that in case some of you were reading through the textbook and see that note, okay? And here we circle back to Zachary's answer about the secondary bonding. So you could see here that there are covalent bonds in between the carbon atoms, and then that there are secondary bonding in between the chains. And so you could see here that this is a quite open structure. There's a lot of space. They're not as packed in as you can see. So that also will explain a lot of the mechanical properties that we'll see. Yes?
Quick question. Could you go back to the previous slide?
Mm-hmm.
So when you say that there's 60 kilojoules per mole release, are you implying that the polymerization of this polymer is spontaneous or not?
It requires a catalyst because you have to initiate the radical formation. If you just add a mer and another mer, most of the reactions, okay, particularly with polyethylene, does not happen. You need to initiate that radical formation, and that requires a bit of energy. Sometimes it's just a little heat and the catalyst that will get that form that radical for you. All right, I saw a hand and then a hand. Yes. Yes.
So why is there energy released overall if there's more energy going into forming bonds than there is energy coming out of breaking bonds in that example?
So you have two carbon-carbon bonds that are being formed.
Does that consume energy?
Well, it is being released, right? You're releasing 60 kilojoules.
Why does that release energy in forming the bonds?
What do you mean? So, sorry, I don't think I...
So forming atomic bonds, doesn't that consume energy typically, or does that release energy typically? You need energy for reaction to form material. So if there's less energy being released from breaking than there is being used forming, why is there overall 60 being released?
You mean why is it 60 exothermic?
Yeah.
So, because you're forming two carbon-carbon bonds. Okay,